Welcome to another deep dive. Today we're going to try to get our heads around something big, like really big, the fundamentals of physics.
Yeah, that's right.
But don't worry, no pop quizzes on formulas today.
No, sir.
We're aiming for something even cooler, like those mind-blowing basics that just make you see the world a little bit differently.
Oh, I like that.
So we're diving into your stack of sources here.
Yeah.
We've got, let's see, an 11th grade physics textbook, and then a whole chapter from this, the Physical World book.
Nice.
And one of the first things that kind of jumped out from like the textbook, definition-wise, right? Physics, it's the study of nature
Right.
and natural phenomena.
That's it.
And physicists are basically like detectives
I was going to say, yeah.
trying to crack this case and figure out the rules of the universe.
Yep.
But that's kind of what makes you wonder, if it's like everything,
Right.
where do you even begin?
Right. So our textbook here actually goes into that a little bit.
Okay.
Because one of the first things it does is lay out just the vast scope of what physics covers
Oh, okay.
on a range of scales that is just, it's truly mind-boggling to think about.
Okay.
I mean, we're talking about the difference between something as tiny as an electron
Okay.
and the entire observable universe.
Wait, hold on. So you're telling me that there's a connection between like something smaller than an atom and like all of space?
Absolutely. I mean, the difference in scale between those two things, right? It's practically impossible to even picture.
Yeah.
Think about it this way. It's a factor of 10 to the power of 40.
Like one with 40 zeros after it.
Yes, exactly.
Okay, my mind is officially blown.
Yeah.
That's incredible to think about. Something that tiny and something that massive are actually under the same like basic laws of physics.
It is. That's the beauty of it, right? It's like this invisible web connecting everything.
Right.
And physics is how we kind of try to understand the threads of that web.
So then if physics is like this secret code to the universe,
Yeah.
what are those like cheat code rules that we need to know?
I like that. That's good.
Thank you.
So this is where it gets really cool. This is where we got to start talking about fundamental forces of the universe.
Okay.
So we're talking about the forces that are responsible for literally every interaction, every bit of motion and energy
Okay.
we experience as beings in this universe. And you know what? There's only 4.
Hold on. Just 4. It
Yeah.
seems like way more than that.
Right. You'd think so, right? You'd think it'd be way more complicated than that, but no. There are 4 fundamental forces,
Okay.
and it sounds deceptively simple when you put it that way.
Right.
But trust me, the implications are huge.
Okay.
So let's start with the one that's maybe the most familiar. Let's talk about gravity.
Okay.
So this is the force that's responsible for, the old saying, what goes up must come down.
Right. That's why we're all stuck to this planet.
Exactly. That's why apples fall from trees. That's why the moon orbits the Earth.
Right.
But it also governs, like, on a cosmic scale, how planets orbit stars, how galaxies interact. It's a big deal.
Okay. So yeah, gravity is a big deal,
Huge deal.
but it's just 1 out of 4.
1 out of 4, that's right.
So what else is out there shaping the universe as we know it? Okay. So gravity is a big deal,
Huge deal.
but it's just 1 out of 4, right?
1 out of 4, that's right.
So what else is out there shaping the universe as we know it?
Well, the next force is one that you're experiencing right now, even though you probably don't even realize it.
Okay. Now you've got me intrigued. What is this mysterious force?
Electromagnetism.
Okay.
And this is the force that's responsible for, well, so much of what we experience in our everyday lives.
Okay.
I mean, it's why matter holds together.
Okay.
It's why you can't walk through walls. And it's why magnets stick to your fridge.
Wait, hold on a sec. Are you telling me that those little magnets holding up my grocery list on the fridge are using the same force that, like, holds atoms together?
I am saying that that's exactly right. Electromagnetism is far, far stronger than gravity. But it works. It really only works over these very short distances.
Right.
But think about it this way. When you pick up a book, right?
Yep.
You are using electromagnetism to counteract the gravitational pull of the entire Earth.
Whoa, so it's like my muscles versus the Earth,
Yeah.
and electromagnetism is what's giving me the edge here.
Yeah, you got it.
Okay, that is mind-blowing.
Yeah.
I had no idea.
It's pretty incredible, isn't it?
It really is.
And it gets even wilder, right? Because electromagnetism, this is also the force that's responsible for light.
What's...
Electricity, magnetism, it's like the ultimate multitasker of fundamental forces.
Okay, so I'm starting to see why physicists get so excited about these underlying connections.
Right.
Like that's really cool. So we've got gravity, we've got electromagnetism, that's 2 down, 2 to go.
2 to go. You got it.
Right, what else is there?
All right, so now we're going to zoom in even further
Okay.
to the heart of the atom, the nucleus.
Okay.
And this is where we encounter the strong nuclear force.
The strong nuclear force. That sounds pretty intense.
It sounds intense, and it is intense.
Right.
This is the strongest of all the fundamental forces, and this is the force that's responsible for binding protons and neutrons together in the nucleus of an atom.
Okay.
Which, if you think about it,
Thanks,
is kind of a
Karen.
crazy thing because those protons, they're all positively charged, right?
Right.
So they want to repel each other.
Right, like trying to force the same ends of two magnets together?
That's exactly what it is. Like, imagine trying to squeeze those magnets together. It takes a ton of energy to overcome that repulsion.
Right.
And yet the strong force manages to do it.
Yeah.
And it holds that nucleus together.
Okay.
And it forms the basis for, all the matter that we see around us.
Yeah.
It's incredible.
Okay, so that's pretty impressive. Like, that's a lot of strength.
Oh, yeah.
But it's working on, like, a seriously small scale.
You got it.
Yeah.
Incredibly strong, but only over incredibly, incredibly small distances, like within the nucleus of the atom itself.
Right.
Like if you think about the scale of an atom, right, like say a football stadium,
Okay.
the nucleus would be like a pea on the 50-yard line.
Oh.
And that's the scale we're talking about, where the strong force is doing its thing.
Okay. All right. That's a good way to picture it. So strong force, it's reigning supreme in this tiny little kingdom of the nucleus.
Yes.
But what about that last force, that last elusive force?
Ah, yes. The weak nuclear force.
What does it do?
This one's a little more mysterious, a little more subtle. It's the force that's responsible for radioactive decay.
Okay, radioactive decay. I mean, it sounds kind of ominous. What exactly is going on there?
So it's not as scary as it sounds.
Okay.
It's a natural process where certain atoms, like, for example, uranium,
Oh.
they're what we call unstable.
Right.
And they will spontaneously change their structure by emitting particles. That is radioactive decay.
So the weak force is kind of like the master of transformation in atoms.
That's a really good way to put it, yeah. It's like the weak force is kind of like whispering to these unstable atoms, hey, you might want to rearrange yourself a little bit, change things up. And even though it might seem less impressive,
Yeah.
less powerful than something like the strong force,
Yeah.
it plays a crucial role in understanding like how elements form, how stars evolve. It's a really big deal.
Wow. So these four forces, it's like they're in this really intricate dance, shaping everything from the biggest galaxies to the smallest, tiniest particles. It's kind of amazing. How do physicists even begin to like unravel all of this? It's incredible. There is intricate bands shaping everything from the biggest galaxies to the smallest, tiniest particles. It's kind of amazing. How do physicists even begin to like unravel all of this? It's incredible.
Well, they're like detectives looking for clues, right? And one of the biggest clues they have is this idea of unification.
Unification. Okay, so what is that? Break it down for me.
So basically, it's this really cool idea that a lot of things that look like totally different phenomena are actually governed by like the same underlying principles.
Right.
It's like finding like these hidden connections in the universe's like grand design, right?
Yeah. So it's like those moments in a movie where the detective, they've got all the photos up on the board.
Yes.
And they're like, wait a minute, and they start connecting everything with the red string.
A great example of this is like Newton's law of universal gravitation.
Right.
Before Newton, people thought like the motion of the heavens and like the motion of objects here on Earth were like two totally separate things.
Right. Completely unrelated.
Right. And then Newton comes along and shows that they're both governed by the same fundamental force, gravity.
So gravity went from being like this mysterious force to the thing that explains why planets orbit and why my pen falls off the desk.
Exactly, precise.
That's a pretty big aha moment.
Yeah, it really, really is. And then there's Maxwell, who unified electricity, magnetism, and light.
What?
In the 19th century, showed that they were all different aspects of the same fundamental force, electromagnetism.
Oh, wow.
I mean, that was huge.
That's like some seriously elegant physics right there.
Yeah, beautiful stuff.
Like finding those connections.
Yes.
Realizing there's a bigger picture. I'm starting to get why this whole unification thing, it's a really big deal for physicists.
It's the ultimate quest, right? To find like that single framework that can explain everything in the universe.
A theory of everything.
A theory of everything, exactly.
Wow, okay. So, even if we find these unifying theories,
Yeah.
with all this talk of forces and interactions and everything else, it seems like the universe would just be this chaotic mess.
Right.
How does anything stay consistent?
That's where conservation laws come in.
Conservation laws. So
yeah.
It's like environmentalism, but on a universal scale.
Well, not exactly, but I like how you're thinking. It does involve a kind of balance, right?
Okay.
Conservation laws are telling us that there are certain quantities in a system, right?
Okay.
That always remain constant,
Okay.
even while other things are changing.
Okay, I need an example because I don't quite... What kind of quantities are we talking about?
Okay, so think about energy for a second.
Okay.
So you've got the law of conservation of energy, and that states that energy can't be created.
Okay.
It can't be destroyed.
Yeah.
It can only be transformed from one form to another.
So, like, if I burn a piece of wood,
yeah,
the energy that was stored in that wood, it doesn't just disappear.
Yeah, right.
It gets turned into, like, heat and light.
Exactly.
Right.
The total amount of energy in the system is the same, even though it's changed forms.
Got it.
And that applies to everything from, like you said, burning a piece of wood, chemical reactions, to the motion of galaxies. This is a big deal.
Wow. Okay. So energy is one of these fundamental quantities that has to always stay balanced.
Exactly.
Okay. What else? Sure. What else is there?
Well, there's mass. So classically, we thought that mass also couldn't be created or destroyed.
Okay.
But then Einstein came along
boy.
and kind of shook things up with his famous equation, EMC.
Right, the one everyone's heard of, even if they don't know what it means.
Right, exactly. But what that equation is really telling us is that mass and energy they're two sides of the same coin.
Okay.
They're interchangeable. And that was huge.
Right.
Because it changed how we understood the universe.
Yeah.
And it led to some really, really profound technological advancements, right? Like nuclear power is based on this idea.
Wow. Talk about a game changer. So we've got energy, we've got mass. Are there any other cosmic rules of accounting that we need to know about?
There's a couple more that have to do with motion, like conservation of linear momentum, conservation of angular momentum, but they all really kind of come back to this idea that even though the universe is this incredibly complex, constantly changing place, right? With forces interacting, energy transforming, there are these fundamental quantities that always remain constant.
So it's like there's this underlying order.
There is.
There are all the chaos, and that's like the rule book.
It's the rule book. You got it.
Okay. Wow. When we started this whole deep dive, I thought physics was going to be all about complicated formulas and abstract theories.
Right.
But it's so much more than that.
It is.
It's about uncovering these hidden connections in the universe.
Absolutely.
From the smallest particles to the largest galaxies.
I love it. It's been so much fun. This has been a great conversation.
It really has. And it's been amazing having you here as our guide on this journey into the world of physics.
Yeah.
But if we had to leave our listener with just one final thought.
Okay.
One kind of lingering question to ponder.
Okay.
What would it be?
Oh, it's a tough one. But I think I would ask, so if we as humans, as physicists, if we do eventually find this theory of everything,
right,
this ultimate unification of all the forces, how might that change our understanding of ourselves and our place in the universe?
Right.
Will we have finally cracked the code?
Now, that is a question worth pondering. A huge thank you to our expert for taking us on this incredible journey into the heart of physics.
Thank you for having me.
And to our listener, we hope you enjoyed this deep dive as much as we have. Until next time, keep those minds curious and keep exploring the wonders of the universe.